All right, so in this video, we're going to focus a lot on the mechanisms of initiation. Recall that initiation is going to be a process in which we start with 0 radicals and we end up with multiple radicals. And this generation of radicals is going to be the very first part, the very first step in our reaction mechanisms. For our free radical chain reactions, we are going to have multiple different parts. We're going to have an initiation, a propagation, and a termination. And all 3 of those are going to be going together in order to make our entire mechanism. Right here, we're just going to be focusing on the very first part. So there are a variety of different ways in which you can have your reaction conditions. If you remember all the way back from an earlier video, we mentioned that there's a bunch of different reaction conditions that you can do. The big difference between most of these are going to be the initiation step. The propagation and the termination is going to follow the exact same, but the initiation is going to be totally different. So we're going to focus on each of these different methods and think about ways in which you can initiate. So one of the first ones is through a peroxide. So a peroxide is going to be a species that has 2 oxygens single bonded to each other. So oxygen single bond to an oxygen with 2 other things. One of the most common is going to be hydrogen peroxide, which is H2O2. Now, these peroxide species are really unstable, so they will break up. If you use heat, which we show as a triangle, that will happen very nicely. This process is known as pyrolysis, and in these we are going to show a homolytic bond cleavage. So a homolytic bond cleavage of a peroxide is going to happen at the unstable bond, which is between those 2 oxygens. And in this case, we are going to give 1 electron to the oxygen on the left, 1 electron on the oxygen to the right. And that's going to be an even sharing of those 2. So overall, we're going to generate 2 of our radical species. And we'll show that as a radical species because we have a single electron rather than a lone pair on the oxygen. So that oxygen has 1, 2, 3, 4, 5, 6, 7 valence electrons around it rather than the preferred 8. And this is going to be a species that's then going to go on and do some other chemistry later. So the key thing is, and we see this as initiation. On the left side of our reaction, we have 0 radicals, and on the right side, we have multiple radicals. So that process is a example of an initiation, a generation of radicals. Our second type of initiation process is using an azo compound. One of the most common is AIBN, which we have shown here. I have the full name over on the side: azo bis iso butyl nitrile. AIBN and a lot of the other azo compounds are really good at generating radicals that are super stable. Even though AIBN is a really complicated structure, you have a nitrogen that has 2 bonds. They're double bonded nitrogen. The double bonded nitrogen is the azo part of this azo compound. And the reason that these azo compounds are so good is this will generate nitrogen with triple bond between them, and that's N2, which will just bubble off as a gas. With it, it's going to be on each of the sides, it's going to have a cyano. Cyanos are really good electron withdrawing groups, as well as a tetrahedral spot. That's going to be a spot that is going to be super substituted and really good at creating a really stable radical. So underneath, I kind of have like a drawing that doesn't have all the CH3s and CNs kind of written out as bonds, and both of those are equivalent. If you take any azo compound like AIBN and expose it to the right conditions, most of these are going to be heat activated. Some can also be light activated. I don't remember off the top of my head the exact temperature for AIBN. I think it's somewhere around the range of like 70, maybe it's 50. If you put it to the right temperature, this will undergo a variety of homolytic bond cleavages. The 2 most reactive bonds are going to be the ones on the left and right side of your azo. That's the N2. And in there, you'll send 1 radical each to that kind of central carbon, and then the other one will actually come in to generate N2 gas. So there's a total of 2 sets of homolytic bond cleavages in here. That will go to make N2, which is a gas and will bubble out, as well as 2 of your reactive species. And your reactive species are going to be super stable radicals because you'll see that this is a tertiary, because I have 1, 2, 3 bonds that are going to be surrounding that radical. Reason that AIBNs are really nice is you do a single reaction. It can be controlled by temperature, so these are going to be more stable than like your peroxides that we showed above. And you're going to be generating 2 super stable radicals, and the N2 will just bubble off as a gas. So those are going to be your second main type of initiation that you can do. And there's a bunch of other derivatives for azo compounds, some that can be water soluble, some that will have different conditions and things of that sort. The next set are going to be ones that can do light irradiation. One of the first is going to be NBS. NBS stands for N-bromosuccinimide. Making sure I spell this right. Which we call NBS. So NBS is going to be a way in which we can generate radicals that are going to be less toxic and corrosive than our liquid bromine. So NBS is a 5-membered ring that has a nitrogen heteroatom, 2 carbonyls, and then that nitrogen being bonded to a bromine. Now, in this NBS, the bond between the nitrogen and the bromine is going to be the most reactive. So this can cleave to generate your succinimide radical, as well as a bromine radical. Now, in terms of stability, that succinimide is actually a super stable radical because you have a bunch of resonance that you can do. You can resonate it on both of the sides with the carbonyl. So you can actually spread that radical off 1, 2, 3, 4, 5 different. So you have a ton of resonance stabilization that exists. Outside of NBS, you can also just take liquid bromine. So if you just take bromine and expose it to light, it will also undergo homolytic bond cleavage and generate 2 reactive bromines. And here, this kind of shows you, kind of zoom out, all 4 of those kind of ones that we showed originally. Using a peroxide, using an azo compound, using a succinimide, or just using Br2 and light. And all of these are going to be methods where we initiate. So we have 0 radicals as a reactant, and then 2 radicals as a product. The nice thing is, no matter what your reaction is, your initiation is going to be one of those 4 steps. The things that will change a lot are going to be the propagation and the termination. And in the next video, we'll walk through a full mechanism for the bromination of kind of like a simple like methane. But these are our kind of 4 main initiation steps. We will either use our peroxide generation, AIBN, NBS, or Br2 and light. And those are going to be our 4 main starter mechanisms for our initiation.